So in this model, I want you guys to please create a new model in the folder for week 3. We are going to call it Sandy Moss Electrics -parallel locations. So what is the structure of this model? PC boards come into manufacturing, material receiving, and then they go to inspection, and then they go to packing, and then they exit the system. The time in inspection and the time in packing is given to you. PCB boards arrive every 12 minutes, exponentially distributed. So that's all we know about the inter-arrival time. So they arrive every 12 minutes, exponentially distributed. One important piece of information is that we have 3 inspection machines working in parallel. What does that mean? That means when a PC board comes, they go from material receiving to any one of these 3 inspection machines, and then they go to packing. They just need to get processed in one of them, and that's all is needed. And then they can go to packing. Okay, so that's what we call by parallel locations. There are 3 of them, they're working in parallel. Entity can go to any one of them, and then they go to the next location. The same scenario that happens in a bank, the same scenario that happens in a call center. When you call or when you go to a bank, you need to talk to only one agent and then you're good to go. But there are many agents that are working in parallel and they're doing the same job. Those are the scenarios where we have to capture parallel locations. Here, I have 3 inspection machines that are working in parallel. When the entity comes, the entity can go to any one of them and then go to the next machine or just leave the system, depending on what is the structure of the process. Okay, so we want to learn how to take care of parallel locations. So what I want you guys to do, please create a new model in the folder for week 3. Name your model as Sandy Moss Electrics -parallel locations. I want you to create 3 locations, 1 for material receiving, 1 for inspection, and 1 for packing. We will talk about how to take care of the parallel location parts. Make sure the material receiving has capacity of infinity and inspection and packing have capacity of 1. I want you to create 1 entity for PC board and also capture the arrival of PC board. We do the processes together. Okay, so please do that. I'll call your names to see your progress. And when you are finished with these 3 first steps, please let me know. We do the processes together. Okay, guys. Okay, so we have the locations, material receiving, inspection, and packing. Material receiving has capacity of infinity, the rest have capacity of 1. I didn't assign any queuing rule for material receiving. Just keep that in mind. It's not a big deal, but it affects the similarity of our results. But just keep that in mind. If you have it first in, first out, that's fine too, but it may changes our results. Entities, PC board, arrivals. I get 1 PC board at a time from the start of the simulation. For as long as I run the simulation, inter-arrival time is 12 minutes, exponentially distributed. Simple, easy arrival process. Okay. And for the locations, if you go back to the locations, so here you see unit 1. So that means I have 1 material receiving, 1 inspect, and 1 packing. Okay. However, for the inspect, I have 3 of them that are working in parallel. So how should I capture that here? I have to change the number of units to 3 because units shows the number of parallel locations. If I have 3 inspections that are working in parallel, I have to put units 3 to capture that. And once you do that, you see simulation will create 3 inspections for you. Inspect 1, inspect 2, inspect 3. Simulation will, ProModel automatically will take care of that. So you have 1 inspection that shows overall what happens in the inspection process, but it includes basically 3 inspection machines that are working in parallel. And also in your layout, you see that there are 3 inspection machines here. So if you have parallel locations, you can change the number of units, increase it to 2, 3, or as many parallel locations you have, and that will take care of the situation. Okay. So that's how we are going to take care of the parallel locations in this model. Now let's go to processing. So in processing, the entity is PC board, which is now at material receiving. On routing, on the exit, the entity which is PC board comes out and it goes to inspect. You see here, I do not have inspect 1, inspect 2, inspect 3. I only have inspect. So all I can do is just to say it goes for inspection. Simulation will take care of it behind the scene, that when entity goes from material receiving to inspection, which inspection machine the entity goes to. Simulation will take care of that for us. All we need to tell to the simulation is that after material receiving, we go to inspection. That's all we need to say. Okay. Obviously, there's no processing in material receiving, so I don't need to do anything for operation. Next, PC board goes from inspection. Again, there is no inspection 1, inspection 2, inspection 3, just inspection. Goes from inspection to packing. And lastly, PC board goes from packing to exit. What is the processing time at inspection?
And 10.3.
And 10.3. And what is the processing time at packing?
8 and 5.2.
5.2. Okay. So simulation will take care of it behind the scene, that when entity goes from material receiving to inspection, which one of these inspection machines that are working in parallel will end up working on that entity. We don't need to worry about that. Let's run the simulation for 160 hours. Okay, I got about 797 exits. The entities have been in the system for about 17 minutes. And here, you see, I have percentage in operation for inspection 1, for inspection 2, for inspection 3, and then for also 1 for inspection. Can you tell me what is it, this last one?
Is it just the average of inspection overall?
Yes, the simulation also reports 1 as the average of these 3 inspection machines, and just put it that as inspect overall. I also want you guys to pay attention that inspect 1 has more time in operation, 45%, and then inspect 2 comes to 24%, and then inspect 3 goes to 12%. So inspection 1 has been processed more, or inspection machine 1 has been used more compared to inspection machine 2 and inspection machine 3. So what does that show us? It shows us that when the parts have come to get processed, they have gone to, if all of them have been idle, they go to inspection 1 first. If machine 1 is busy, then they go to inspection 2. If machine 2 is busy, then they go to inspection 3. That's why the operation time or the processing, that's why inspection 1 has more time in operation compared to inspection 2 and compared to inspection 3. What I want you guys to pay attention to is that this rule that when the entities come, they should go to inspection 1 first, and then if it was easy, then inspection 2, and then inspection 3. We can change this rule if we want to. What if I want to assign the entities to the inspections by turn? I want to assign the first one to the first inspection, the second one to the second, the third one to the third, the fourth one to the first, the fifth one to the second. I want to just take turn. Or what if I just want to assign them to these inspection machines randomly? We can change that rule in the simulation. Where do you think I have to go to change the rule by which these entities are assigned to these inspection machines?
In the location rules, the third option?
In the location, it's a location characteristic, right? We are playing with the inspection machines. It's the location thing. So I have to go to location to change this rule. So to be able to do that, we are going to click on the rule. So click on the inspection, inspect, and then here click on rule. This window opens that we worked on in previous session. This time we are going to stick to this last column, selecting a unit. You see first available, that's the rule that is always chosen by default when we have multiple parallel locations. First available, and that's why you see the word first here, that shows first available. First available is exactly the rule that we just talked about. The entities always go to the first machine. If it was busy, to the second, if it was busy, to the third, to the fourth, and so forth. So they always go to the first one first, if it's idle. However, there are other rules here as well. By turn, I want to assign the entities by turn. I want to assign entities to these inspection machines just randomly. There are other options, most available capacity, longest empty, and so forth. So we'll go over them later in future models, so we will get the chance to know what they mean. But for now, there are a couple that are easier to understand, assigning them to these inspection machines by randomly or by turn or first available. So let's try a couple of those. Let's try random. Change the selecting a unit rule to random. Press OK. And when I do that, you see here, instead of first, now it's random. It changes. Run it one more time. Okay. You see here, since it's random, everyone has gotten about the same operation. It's the same number of entities. So each one of these inspection machines has about the same time in operation because they got about the same number of entities to process. Okay. If I go and check their utilization, location summary, utilization for inspect 1, 2, 3, you see their utilizations is about 33% for each. So they have about the same utilization. And on average, inspection machine has about 33% utilization. Okay. Make sure that you guys are mindful about the fact that the utilization that I see here is the sum of what and what?
Is it the block time and then the operation time, right?
Exactly. The utilization is the sum of the time in operation and the block time. The time in operation is about 28%. The block time is about 4%. That's why we see about 32, 33 utilization in the location summary table. These numbers here. Okay. So be mindful of these numbers and how they have been calculated and what do they mean. Okay, always. So yeah, so that's where we can go change the rules on how entities are assigned to these parallel locations and make sure to capture the detail of the system you're trying to analyze as clearly as and as closely as possible. Okay, so now I want to tell you how to also capture parallel locations in a model, but in a different way. Okay, so this is what I want you guys to do. Save this model as a new model in the same folder. But at the end of the name, put second method. Okay, save the same model as a new model in the same folder, but at the end of the name, put second method. So we are still going to capture parallel locations, but using a different method. What I want you guys to do is in the location, change the unit to 1. Okay. And add 2 more inspect machine. So basically, I want to put 3 separate locations for inspection 1, inspection 2, inspection 3. So do that for me. So change the unit to 1. So that's 1 inspection machine, but I want you to add 2 more for inspection 2 and inspection 3. So create 3 separate locations for inspection 1, 2, 3. They are still parallel location, and we'll learn how to do this part. Okay, I have 3 separate locations. 1 for inspect 1, inspect 2, inspect 3. So I have 3 separate locations as opposed to previous one when we created just 1 location and changed the units to 3. Here I created 3 separate locations for these 3 parallel inspection machines. Okay, that's change 1. Entities, I'm not going to change anything. Arrivals, I'm not going to change anything. For processes, let's delete everything we have here. And make sure to save, guys, as we go forward. Okay, so location, we added 3 separate locations for this inspection 1, 2, 3. No change in entities, no change in arrivals. Processing, delete everything. We are going to do everything from the start. So entity, which is PCB board, and is now at material receiving. Now entity wants to go to these locations, inspection 1 or 2 or 3. So PC board, when I click on destination, you see, now I see 3 inspection, inspection 1, inspection 2, inspection 3. So now I say, okay, let the entity go to inspection 1. Press enter on the same routing, on the same line. PC board may go to inspection 2, or PC board may go to inspection 3. So I put all these 3 possible destinations for the first line. When the entity leaves material receiving on the routing section, it may have one of these 3 possible destinations, inspection 1, 2, or 3. Just I specify all of them. I want you guys to pay attention to one thing. You see here the column BLK is abbreviation for block. So these are all part of one block. We will learn later that when we create these new lines, we can click on the rule and then this box opens. And here if I, by accident, check start new block, press OK, then this number 2 is created, which means this line is a different block. I do not want that to be the case here. Later, we will learn to write code here in the operation, and we will write if then else codes, and we say, okay, if this is the case, go to block 1, otherwise go to block 2. For those scenarios, I need to specify different blocks. We will get those, we'll have a bunch of examples related to those. But here, I don't want that to be the case. I do not want this to be a new block. So make sure start new block is unchecked. And all of these are just part of one block. So basically, this is just one destination. What then the entity ends up is going to be to go to instruction 1 or 2 or 3. Okay. Then Next line. Let's assume entity ends up at inspection 1. Where does it go from there?
Packing.
To packing. And where does it go from packing?
To the exit.
Exit. What is the processing time at inspection 1? Normal, 10:3. Okay. Next line. Let's assume the entity ends up at inspection 2. Where do we go from there? We still go to packing. After we are done at inspection 2, we go to packing. Do I need to tell the simulation where do I go from packing?
No.
Because?
You already told it that you go from packing to exit.
Exactly. I already told the simulation that if you happen to be in packing, then you have to go to exit. Simulation already knows that. So I don't need to specify that again. And next line. PC board. Let's assume this time it has ended up at inspection 3. And then where do we go from there? Go to packing. And again, I don't need to tell the simulation again, where do I go from packing? Because I already have mentioned that once. You can do it. You can repeat this line 3 times. You don't get error, but it's absolutely unnecessary. And make sure that processing time on inspection 2 and inspection 3 is defined as well. And also on packing, processing time was normal, 5-2. Okay. So in the first line, material, we go from material receiving to one of these destinations, inspection 1 or 2 or 3. We write them in parallel. Then in the next lines, we consider all possible scenarios. What if I end up at inspection 1? Where do I go from there? What if I end up at inspection 2? Where do I go from there? What if I end up at inspection 3? Where do I go from there? And then in all of these inspections machines, I end up at packing. So if I end up at packing, where do I go from there? I only need to specify that once and I will be fine. And we are going to run the model again for 160 hours. Okay. So we had about the same number of PC boards exiting the system. We have the percentage of in operation for inspection 1, for inspection 2, inspection 3. As you can see, again, inspection 1 has worked on most parts, then inspection 2, then inspection 3. If all of them have been idle, parts have gone to inspection 1 first. And then if it has been busy, they have come to inspection 2, and then they have come to inspection 3. As you can see, I do not see a separate line for inspection overall. There's no average inspection anymore. Simply because simulation does not do that anymore. Simulation just consider these 3 as 3 different locations. We told the simulation here in processing that they are working in parallel, and that's all that matters. But simulation is not going to know to consider one inspection for the average of all these 3 parallel locations and so forth. No, it's not going to report such a thing anymore. If you need that, you have to calculate it yourself. If we define the parallel units using the first method that we just learned, yes, you get that from simulation, but not in this method. So now, Similar to previous method, what if I want to use a different rule for assigning entities to inspection 1, inspection 2, and inspection 3? I don't want it to be first available. I want it to be random or by turn. Where do you think I have to go to change that rule? So in this scenario, we have to change the rule in processes. Here, when I identify them as parallel location, that's where I have to change the rule. Here, if you, for the first line, if you click on the rule, this window opens. There are a bunch of options here. We will learn them throughout the class. We'll learn all of them. Some of them are related to the rule for parallel locations. First available again. And this number 1, first one, is because of that, representing first available. When you see first represents first available. If I want to change it to random, here I have the option random. If I want to change it to by turn, here I have the option by turn. So this time, let's implement the by turn option. Instead of first available, where I show first here, I'm going to choose by turn. But we have to do it for all of them, all these 3 lines. So check by turn, press OK. You see it's now changed to turn as opposed to first. Make sure to make the change for other locations too. And make sure to save, guys, as we proceed. Everyone change the rules? So just click on the rule and pick the right rule that we want. If you're done, run the simulation one more time. Now you see for inspect 1, inspect 2, inspect 3, almost they have about the same percentage time in operation. And if I look at their utilization as well, location summary, 32, 31, 31. So they have about the same utilization as, which is the sum of percentage of time in operation and percentage of time blocked. So yeah, so your numbers can change. It is possible that when you change the rules, the total exit changes or the time in system changes. They actually can happen. So this actually is one of the things that we can play with to see which one of these rules ends up with more processing more parts or less time in the system. Later, to be able to do that, we actually are going to run many replications for each method, and then we will learn how to check that statistically if one method leads to more exits and less time in the system compared to others or not. So we'll check all of that. So it's possible that when you change the rules, your numbers change slightly. Okay. Now, I have a question for you guys. Tell me what is the disadvantage of this method compared to the previous one that we just learned?
A lot more tedious.
More tedious, yeah. I would, yeah. Everything you said is valid, but I would say more tedious is probably a good description of the system here. Before I continue, everyone can hear me fine?
Yes.
Okay. Yeah. So here, as you can see, I have 3 inspection machines. I have to write for each one of them separately. If I end up here, where do I go from here? If I end up in inspection 3, where do I go from here? If I have 10 parallel inspection machines, I have to run for I have to write for each one of them. Where do I go from there? So it's more tedious than previous method. However, there is an advantage associated with it. And the advantage is that it is more flexible. If for some reason, let's say inspection 1 takes more time to process a part compared to inspection 2 and 3, I can definitely do that here. If inspection 1 takes 12 minutes to process a part, perfect, no worries, I can specify that. Still, there are parallel locations that are doing the same thing on the part. They are working in parallel, and the part needs to go to one of them only. But somehow the first machine is a little older than the other ones. It takes a little longer to process a part. I can specify that here. But with previous method, I could not do that. In previous method, I just said parts go from material receiving to inspection, and the time in inspection is 10:3. That's it. If one of the inspection machines has more time or less time, I cannot make that change. So in previous method, those parallel machines are truly identical. But in this method, yes, it is a little tedious. However, it's a lot more flexible. If these parallel machines end up with different processing time, you can capture that. If somehow after the first machine, the part doesn't go to packing, just goes to the exit, you can capture that. But in previous method, that wasn't the case. After the part goes to inspection, after inspection, all of them go to the whatever destination is we are going to specify, all of them. No matter if you go to inspection 1 or 2 or 3, all of you end up with packing or whatever we define. But that's not the case here. If after inspection 2 and 3, they go to packing, but after inspection 1, for example, they go to exit, we can specify that as well. So this method is more tedious. However, it can give you the option for capturing a lot more flexibility in your model. So be mindful about that and pick the right methods depending on the complexity of the system that you are developing. Now, we are going to learn the concept of movement time between the locations. So far, every model that we develop, if the parts go from one location to another, we assume that that transition happens in no time. So the part immediately goes from material receiving to inspection machine, any one of them. When they're done at inspection machines and they want to go to packing, that transition happens in no time. Immediately, if the packing machine is empty, they immediately go to the packing machine. However, in real world, that's not always the case, or most of the time it's not the case. If there are two locations, two machines, they have some distance from each other, and it takes time for one part that is done in the first machine to go to the second machine. So there is some time associated with this movement going from one location to another. So that's the movement time, or that's the move time we want to be able to capture, because that makes our model more realistic. So to be able to do that, this part of the processes move logic is the part that helps us to capture any move time that may be in our model. So let's assume here there is 3 minutes fixed, 3 minutes move time for going from any location to the other, going from material receiving to any one of these inspections, and going from any one of these inspections to the packing. Okay, let's assume there is 3 minutes fixed move time. We can identify that in the move logic window. So here I can write move for 3. Or I can write move for 3 minutes, but I don't have to write minutes because the default unit of time is minutes. So if I just write move for 3, that's fine too. Okay. So, and all I need to do is just copy this for all the movements that happens in this system, in every line. And first line, second line, sorry, for the, no, just pay attention that for the line, when the entities go from packing to exit, we do not put any move time, because that exit just is the exit for the simulation model, for the pro model. So the entities leave the system in pro model, but that's not the real exit in the system, in the actual physical system. The real exit in the actual system, or the real end in the actual system, is when they get to packing. That's all we care about when we wanted to model this system. So we do not put any move time when the parts go from whatever location to exit. That's meaningless. We do not put move time for that one. But for anything else, we do put the move time. Okay, so put the move time for anything, all the lines. And here the move time is fixed 3 minutes, so that's all I put. And then run it. Now I see the number of exits. If we go to the entity summary, we also see some time in the move logic, something we didn't have before. So there is also some time in the movement. And as you can see here, entities have only 2 movements, one going from material receiving to inspection, and then from inspection to packing. Each one of them is exactly 3 minutes. That's why the time in movement or in move logic is exactly 6 minutes, and that's correct. Okay. So then the time in system that we see is the sum of the operation time, wait time, if there is any, block time, and move time. So when there is move time associated with moving entities between different locations, obviously that affects the time that the entities end up spending in the system. So we want to be able to capture that. So if we have forklifts to move the parts around, if we have some people who are responsible for moving the entities and the parts around, all those can be considered as move times. Okay. Everyone is good so far?
I have a different total exit with you, Professor.
What is your number?
829.
That's fine.
Okay.
Yes, I got it, I think.
That's fine. One other thing is that here, let's assume I tell you that the move time is not exactly 3 minutes. Is 3 minutes exponentially distributed, let's say. Then all I need to do is to come here and just say move for, let's say, E3. Okay. So then the move time is not fixed 3 minutes, is 3 minutes on average exponentially distributed, or 3 minutes on average normally distributed with standard deviation of 1. Okay, you just write that in N31. So if it's not fixed, if it's random, no worries. You just change it to random values, the random variable. If the move time for between some locations is different from the other, again, no worries at all. Just make sure for movement between every 2 locations, put the corresponding time, and that's all you need to do. Okay. So I put the new move time, which is exponential 3 minutes for all the moves that happens in the system, again, except the one where I go from the packing to exit. I don't need any move logic, any move time for that one. I change the rest of the move times, and then let's run it one more time. Table, entity summary. Okay, and you see here, now the move time is 6.01. It's just a little different because now these move times are coming from the random variable with average 3 minutes. So if one is a little higher or lower than 3, that's fine. Anyway, at the end, the sum is about 6 minutes. Okay, so that's the reason that they are coming from this random variable is the reason that I don't see the fixed exact 6 minutes, which is perfectly fine. But still the move time, the move time is there, and the total time in the system is the sum of the move time, the time in operation, wait time, and block time. Okay. Everyone is good so far? Okay, make sure to save, guys, as we proceed. Now, I want you to save your model as a new model in the same folder. Give me 1 second. And at the end of the name, put move with resources. Okay, save it as a new model, and at the end of the name, put move with resources. Save. Okay. So what do we want to do here? So far, I considered the move time, but I assume there is no resource that does the move. So I again assume that, okay, there is some move time, but the part just goes from one location to the other location itself without any help. However, again, in a lot of real world problems, that's not the case. We have a worker that is in charge of moving the parts around. We have maybe a forklift, a robot, something like that, that is moving parts from one location to another. So if that's the case, then we can capture those as a resource in our model. We want to capture them because then how many resources I have affects the performance of my model. If I only have one person that is in charge of moving parts around, so let's say that person takes one part from material receiving and goes to inspection. And right now, the inspection 2 is done with the part. So the part has to go to the packing, but we are waiting for this resource to come and take the part to packing. However, if the resource is busy taking the part to inspection 1, then the part in inspection 2 has to wait till the guy finally is done. Then the person comes to inspect 2 and then takes the part to packing. Okay, so that resource that is in charge of moving parts between these locations can be a bottleneck itself. If we do not have enough resource, then the parts have to sit where they are done till the resource is finally available to come and take them to the next location. Okay, and if that's the case, which is quite possible in a lot of systems that use resources, either people or forklifts or robots or things like that, when these resources are used for moving parts, it's absolutely possible. If we do not have enough of them, it's absolutely possible that they become a bottleneck in our system. So the process just takes longer simply because there's not enough resource to move the parts around to different machines. So although they are done at one machine, they have to just sit there till the resource is available to take them to the other location. So now we want to see how I still can capture the move time, but here some resources are used to perform the move. So if that's the case, then I need to define a resource. And to be able to do that, I go here, resource. Can you guys hear me?
Yes.
Yes.
Okay,
Yeah.
so I go to the resource. So click on the resource here. You can pick any icon to represent your resource. Say I pick this person and I call it, let's say, worker, or any name you want to give to it. I have one resource and do not change. If I have more than one worker that is doing this job, I can increase the number of units. But here I'm assuming I have only one worker in charge. Okay, do not change anything else. So that's because it's my resource. If you're using the 2016 version of ProModel, you can get to the resources under the build menu. Okay, but if you're using 2018 version, it's perfect. It's right in front of you. Define the resource. And now let's go back to processing again. And here in the move part. Now I'm going to change this code that I wrote. And this time, if you want to have an easier time, I would recommend double click on this window. So let's assume this move window is not open. So double click here on this move window. It doesn't open. I think it happened one more time, and I don't remember what did we do that fixed this. Let's go to Arrival, back to processing. Yeah, it's a glitch. So yeah, so just click on this window, move window, and then this code, this window opens where you can write your code. And as you can see, whatever we wrote in this little window is now shown here, okay? If it happens that you click on it and it doesn't open, like the glitch that I just faced, just go to Arrival or Entities and then come back again and it works. Okay, so what I wanna do here is move for, give me 1 second, let me connect to power. Okay, what I want to write is that move with resource. And when I named my resource as worker. So as soon as I type W, the name of the resource appears here. And I always recommend to pick the resource from this menu, because when you type, there is typo and things, so you get a lot of errors and you don't know what's going on. So when you see the name of the things that you have defined, just pick them from this menu to be on the safe side. So move with the resource, which I called worker, for E3 for whatever amount of time, 3 minutes, E3, normal 3-1, whatever it is. Okay, so move with the resource for this amount of time, then free. This is an important keyword. So all the blue things here are keywords. They have to be there. Otherwise, your system is you are going to get error. Then free is important because what this tells the simulation is that when the resource moves one part from one location to another, then free the resource so that the resource can go to other locations and move other parts. If you forget to put then free, you do not get the error, but you don't see any exit because your resource is stocked in that location and is not available to move other parts. So you do not see any exit, but you don't know what's going on. Okay, so do not forget to put then free if you're using resources to move parts. Okay, so move with, those are keywords. The blue parts are keywords. Your name of the resource, worker here, for whatever amount of time, random or fixed, then free. So that's how we have to write this. So copy that. And we are going to paste it in all the locations where we had a move, except the line where we exit the system. Okay. Everyone is good? Everyone is done? Now let's run the model again. Okay. Now again, if I go to the table summary, to the entity summary, again, I see the time in the system, the move time, and the time in operation and the block time. Okay. Also, you see here, there are some orange part, and when you click on that is percentage weighting, which we did not have before. Previously, we only had percentage in operation, idle, meaning that machine is not working, and then block. But now I have a new part, weighting. And what is the meaning of that? So this represents the scenario when inspection 1 or 2 or 3 are done, they're done with the processing. They are not blocked by the next machine. The next machine is idle. They can send the part to the next machine. However, they cannot do that because the worker is not available to take the part to the next machine. So they are sitting, holding the part, waiting for the worker to come and take the part. Okay? So that's what these orange parts show. That's the percentage of time that the machine, inspection 3 machine, is not be able to work, not because it's processing a part, not because it's blocked by the next machine, but because it's waiting, holding the part till a worker is available to take the part to the next machine. Okay? So be mindful of what these colors mean and how they are interpreted, and potentially if you want to increase them or decrease them. Also, pay attention that if I go to location summary, the utilization that I see here, the utilization that is reported in the last column, is actually the sum of operation time, the percentage of time in operation, and block time, and waiting time. Because in all these situations, the machine is not able to work, either because it's processing a part, or because it has to hold the part because the next machine is busy, or because it has to still hold the part because the resource is not there to take the part to the next machine. So the simulation treats all of these green, pink, and orange parts as utilization. So again, when you report the utilization, make sure you're mindful of how that number has been calculated and which parts are the ones that you want to get rid of and which parts are the ones that you want to increase. Okay. So then we learn to capture the movement in 2 ways. Either move for some time when we just want to capture the movement, not the resources that are performing the movement. And then the other option is when we have some resources that are performing the movement. So in that scenario, this is the line of the code that we have to write. Move with the name of the resource for whatever amount of time, then free. The blue terms are key words. They have to be written in that order. And if you miss any one of them, you get error. Also, when we use this part of the code, this part of ProModel to write the code, you can always use this button you see, compile, to compile the code that you write here. If I press, it just compiles and it says, okay, compile successfully. And that's good because later we will learn, actually we write lines and lines and lines of codes here. So it's always good to compile them right here before we go to the next section of the model or to the next line of the model, because if we just don't do that and leave everything to the end, then suddenly we have tons of errors. But if we compile them piece by piece as we go through the simulation model, it's always better, safer, and takes less time to debug. Okay. Make sure to save, guys, as we proceed. Any question?
Yeah, can you go back to your numbers, Professor? I just wanted to see, make sure mine's the same. All right, thank you. How come on the yours doesn't show the material receiving station right there?
Here?
On the left one, yes. Oh, okay, I see it.
So if you look at here, is single capacity locations. Every location that has capacity of 1. And here is multiple capacity locations. Every location that has capacity of more than 1. they're listed in two different windows.
Perfect. Thank you.
Sure. Any other question, guys? Okay. Make sure to save your model, guys. Okay, so as I said, we are in chapter 4. So next session, we are going to continue with chapter 4. And we are going to learn a very, very important concept on Monday. So make sure you are in class. We are going to learn how to use variables in simulation, and those are going to be used a lot in your simulation models. I have already uploaded homework 2. Your deadline for homework 1 is tonight. And I'll post the videos as soon as I can. Reach out if there's any question. Otherwise, I'm done with the class today, and I covered the materials that I wanted to cover. Have a great weekend. I'll see you guys on Monday.
When is homework 2 due, Professor?
I'll always give a week, so it's a due.
Okay.
Thank you.
Sure.
Thank you. Good weekend.
Sure.
Thank you,
You
Professor.
too, guys. You too, guys. Bye.
Thank you, Professor.
Sure. Bye.
Professor,
Yes.
is it, well, my total exit time is is 819, and I know yours was 777. My average time was like 42.
Here?
So-
That's fine. That's fine.
Okay,
No worries.
thank you.
Professor?
Yeah.
I think like the number of X's, the difference between mine and yours, which is mine is also 819, I think is that in your model, one time in the inspection 1, you changed it to N12.3
Oh, yeah.
for the first inspection.
Yeah.
And we're supposed to keep it at 10 or change it as well?
Yeah, it doesn't matter, honestly.
Oh, okay.
That's not the point.
Okay, and Professor, one last question. So the reading is the chapter 3 lab, right? So the one that starts in page 405?
Yeah, read the homework that I have to assign. I have uploaded on assignment folder. Read the instruction. It has everything.
Oh, okay. All right. Thank you.
Sure.
Professor?
Yeah.
I just checked my other models. They're giving me the report except today's one.
Oh, I see.
I'm not sure what's going on.
Did you uninstall and install or anything?
Yeah, I just reinstalled it, and everything is working fine except today's one. The first one, the data is lost. It's not even coming. And the second one, I can only see the summary.
You mean you can only see the summary? You mean it shows the results, but
Yeah, I'll show you what I got if you have time.
okay.
Yeah, so if I run the simulation and stop the animation, that's all I see.
But click on the table. But you can't show any table. Choose the location summary.
Location summary.
I see. It shows everything, but not the dashboard.
Yeah, the first one. And I can show you if I go to another one, let's say the barbershop one. Anyway, it shows everything fine.
Interesting.
I'm not sure what's going on with today's model.
I don't know either. I haven't ever seen anything like that. Try a simple model right now and just run it again, see what's going on. But the good thing is that at least you get the tables. So
Yeah.
if anything, you can get the tables. You can find numbers from the table.
And try another model right now.
So Yeah, keep me posted on that. And then I would say you can potentially uninstall and install as well in case something is going on. Okay.
Okay. I'll try to do that and keep you posted. Thank you,
Yeah, let
Professor.
me know for sure.
Okay. Have a good weekend, Professor.
You too. Bye.